Okay, so let's start talking about how we're going to tie in all this acid and base stuff that we learned kind of together, right? We've already gone over what an acid is, what a base is, what makes an acid weak or strong, what makes a base weak or strong, how do we calculate, acid, vice versa. What does pH mean? All that good stuff, right? So let's just kind of review a little thing real quick here, right? Like so far what we've kind of done is we've learned that like a solution is, whoops, I went to put acidic. A solution is acidic when we have excess H plus or excess hydronium in solution. Because again, if you think back to the pH scale, remember, right, when we're at 7, we're neutral, because that is that level when we have water creating a certain amount of H plus and a certain amount of hydroxide, and they're in equal value. So we don't have H3O plus in excess, we don't have OH minus in excess. They're in like perfect equivalent amounts, giving us a pH of 7. So we ran into getting like an acidic solution when we had extra or excess H plus floating around. And that's when we knew that there was like an acid present, because there was more H plus than what water would be giving off, right? If it was just water in there, the H plus and the OH minus would be the same, right? We had a basic solution when we had extra OH minus floating around, right? Because if it was just water, the OH minus and the H3O plus would be in the same number, the same quantity, the same concentration, right? So if there was any extra OH minus, that would only be due to the presence of a base, raising the OH minus concentration, making it basic or alkaline. So that's why I'm putting here, we know that a solution is basic when we have excess hydroxide, right? From like a base dissolving here. So what's a neutralization reaction, right? So like as the name kind of suggests, we're actually trying to get the solution neutral, right? We don't want an acidic solution, because when you have excess H plus or H3O plus, what does that mean? Oh, well, that solution is positively charged. There's a lot of positively charged particles floating around. It's not neutral, it's positively charged. When we have a basic solution, if we have excess OH minus floating around, that means that we have a lot of ions floating around that have a negative charge. That solution is no longer neutral. So in a neutralization reaction, we take an acid and a base, and we have to add them in the correct amounts for us to be able to get neutral products and only neutral products. So the point of a neutralization reaction is for there to be no more acid and no more base present. They've perfectly reacted in the correct ratio chemical equation to only give us neutral products. Then and only then will we have a neutral solution. Because again, if we don't add these in the right amount, right? If we have excess acid, well, technically an acid means that we have extra H3O plus. That solution would not be neutral, right? If we didn't add enough base, right? And like the base was limiting, right? The acid would be in excess technically, or if it's vice versa, if we added too much base and like we didn't add these in the perfect amounts, well, now if we have base in excess, it's not neutral anymore, right? We made some neutral products, but there's some extra base floating around that's giving us extra OH minus, making that solution neutral, right? Or sorry, making the solution negatively charged, and we want it to be neutral, right? So a neutralization reaction is kind of a fancy way of saying we're going to take an acid and base reaction and make it go to completion. So I'm going to kind of say that here because that's really important. Neutralization reaction just means that you're adding the acid and base in the correct amounts according to the chemical equation, right, for it to go to completion. Right? So this is just like we did before, right? When we were trying to like look at a reaction and figure out how much do we need of each reactant to make it go to completion. That's what we're doing in this case, but we have an acid and a base, and it going to completion just means that we made the solution neutral, right? We have no more acid, no more base, only neutral products. So think about this, right? Again, like the acid means that we have like some positive charge floating around. This base has a negative charge, right, floating around in it. Our point of this, right, if we added these in the correct amount to balance each other out, right? Then all the H plus from the acid would be able to combine with an OH minus from the base. And we wouldn't have any excess plus charges. We wouldn't have any excess negative charges. We would have added them in the perfect amount to make only the neutral products. So let's actually kind of talk about an example here real quick. Let's look at, just look at a strong acid and a strong base. Let's look at like an Arrhenius example. Let's say that we had HCl plus NaOH. Right? An Arrhenius acid-base reaction, they do not make their conjugates, right? These actually convert over to the H2O and the salt. Right, we're going to look at it to see if it balances. Oh, look, this one's all balanced with 1s. I'll write it in a different color for some of you who like to kind of see the colors. Right? This is like this reaction. And technically, right, since this is a strong acid and a strong base, and we assume 100% dissociation with those, technically it's almost kind of as if this whole thing could lie to the right. In other words, there wouldn't be a whole lot of reversal. When we do like weak acids, weak bases or something, there's that reversal stuff back and forth, right? So like we kind of learned before when we did all those calculations with Ka and stuff, we have to wait until these reactions have reached equilibrium, because this is going to start reacting, right? And it's like if these were weaker acids or bases, we get that back and forth, and we can't really judge, right, if it's like reached equilibrium or not until that back and forth has stopped happening, and that solution or that reaction has reached equilibrium. So what this kind of means, if we were doing a neutralization reaction with HCl and NaOH, what we're saying is we need to make sure, so however much we start with of this acid, right, they react in a 1-to-1 ratio. So I'd have to make sure that I'm adding the same number of moles of this. And how do we find that out, right? We get that with the molarity equation, right? The concentration is number of moles over that volume, right? But we have to make sure that we're adding these in the correct amount so that it goes to completion. So in other words, right, none of this stuff is left. I have only made these two. And if this is all I have present in the beaker, right, water is neutral, right? And this salt, right, technically like combined, right? The NA's +1, Cl's -1, but the salt itself is neutral. Well, they'd be floating around because they're aqueous, but again, that +1 and -1 charge balance each other out, making the overall solution neutral. So that's what we're trying to do with an acid-base reaction. But how do we tell, right, when that neutralization has been reached? Because how we're going to do these things is with something called a titration. And titrations are actually things that like chemists even to this day use. Like people that work at the Fort Dodge water plant, they usually have like a chemist or some kind of lab technician that runs titrations constantly to actually test like the pH of the water and stuff that they're adding into the water. I know people who work at like Koch Fertilizer and CJ Bio and Elanco, and they have chemists and lab technicians that are constantly, like they're taking samples of all their products constantly and testing like pH and looking for like certain concentrations of additives. And they do those with titrations, right? We're doing the high school on a budget titration. We don't have multi-million-dollar machines that does this perfectly, but we set up something called a titration, which is going to require the burettes that we used in the beginning of the year when we were looking at like all the different ways that we can measure liquid volume in this class. And we're going to have our Erlenmeyer flask, also called the conical flask, but we're going to have some unknown either acid or base in here, which is called your analyte or your titrant. I prefer the word analyte because if you can kind of see on here, there's something called a titrant when you say it kind of fast, and a titrand. And when you say those fast, titrant, right? It's really hard to even tell what somebody's saying, let alone, like I almost kind of have to see the spelling because like my mind kind of gets boggled when I hear those. So I usually just refer to this as the titrant and this as the analyte, right? The thing that we are analyzing. So this will always be some like acid or base that, I mean, we know the volume of it because duh, we have cylinders and stuff that can actually measure the exact volume that we put in here. But we have to analyze it to actually see what it is. So we actually do this analyzing through the titration. So if this is an acid that you put in here, right, it's unknown, but you know it's an acid. We don't know which one or what its concentration is, right, what its pH is. We don't know any of that yet. But if this is an acid that we put here, we deliberately fill the burette with a base because we are going to try to force a neutralization reaction to happen. And when that neutralization reaction happens, if we know a lot about this base that we put in, right, like we know its identity because we made it and we put it in the burette ourselves. We're going to know its concentration because we would have either made it or it would have been pre-made. We're going to keep track of exactly how much volume it took to actually, right, neutralize that acid. But if this is an acid down here, again, this is a base. And we're going to use that information, right? Like, again, we're going to know its concentration, right? The pH of it that we used, all that stuff. And something special is going to happen. And we're going to be able to use like a relationship between like an acid and a base. And well, if this is my base, like even if I don't know the acid or whatever, technically like we'll be able to kind of predict how many moles of that acid technically had to be present in order for me to do this. And if I know how many moles of acid I have, I would technically know what my H plus concentration was, right? Think of the acid dissociating and what it breaks into, right? And then if we had what our X plus was, or what our X was, excuse me, you can work backwards and find a Ka. And if you have a Ka, you'd be able to look at a table of values of Kas and possibly identify the acid, so on and so forth, right? So we'll kind of get into that stuff. But again, like we are going to use the fact that like a neutralization reaction can happen between an acid and a base to actually be able to identify something that's unknown. And I just use an example with an acid down here and a base up here. But if this were a base that we put in here, right? So we would have measured out an exact volume, threw it into our E-flask, right? We don't know the concentration or anything yet, but we know exactly what volume we put in, right? Hence known volume, unknown concentration. But if this were a base, we would deliberately be putting an acid in the burette, right? Because we were going to try to force an acid-base reaction to go to completion. So that's how we're going to do these. So let me kind of walk through a couple little things. Well, this next part, I guess, doesn't make... We'll kind of get to these graphs here in a minute. But what we're going to do in these reactions, or these labs, excuse me, is we usually put a special indicator into the analyte, right? The thing that we're analyzing and trying to figure out. And different indicators will turn a certain color at a certain pH. And we're going to learn how to tell, right, like which indicator should we put in, because depending on where your equivalence point would fall, and that pH is going to depend on what type of indicator that you even choose to put in your lab, right? If you choose the wrong indicator to put in here, right, you might miss the color and not be able to figure anything out. But we're going to use an example. I'm going to deliberately use probably this example here with a strong acid and a strong base, so that we can just kind of use the typical one that would turn pink with a pH of 7. So like there's a certain indicator that we can use in this lab, and we're going to do this one for practice. But it's called phenolphthalein, and it turns pink in the presence of excess hydroxide. So in other words, in the presence of a base, this thing will be a really dark, like magenta. I mean, honestly, like it can really be like this color. Like when it's like a pure base in there, like phenolphthalein will turn a solution like this color, this like magenta color here. So we're going to be putting like an unknown, let's say acid in here, and we're going to deliberately drop some drops of that phenolphthalein that turns pink. But again, it only turns that color when it's in the presence of a base. So if we just drop it right now in some acid, we're not going to even be able to see it. It's going to remain clear because that thing only turns color in the presence of a base. So we're going to be dropping in, let's say, some base and dropping this in as we go, right? And if you end up adding too much base, right, and you now have the base in excess, this color is going to turn dark pink, and you're going to know that you technically added too much of this. And we're going to be able to figure out everything we need to know by adding in the correct amount of the base from the burette. Like we have to keep track of the concentration we put in and exactly how much of this it took to actually get this to neutralize. So even though we don't want it to be pink, you're going to know that you're really close to neutralization when like you've been adding in this base, adding in this base. So as you're doing that, let's just pretend, right, that we had NaOH in here and this was like HCl, right? As you've been adding this in, right, because this is in your burette, this is in your flask, right? Every time you put a drop in, right, it's these two have been reacting to produce these, right? But after a while, right, as you keep on doing this, there's going to be less and less and less HCl present in that flask because you've already neutralized some of it and got to these products here. So you're going to start to see sometimes little flashes of pink happen when you're dripping this in. And that's letting you know that the reaction is getting really close to being neutralized, because when you first go to drop this stuff in, this stuff's not turning pink at first because there's so much acid. But when there's hardly any acid left over, right, and that initial splash of base goes into the flask, the indicator you put in, right, like right now there's hardly any acid, right? So floating around that flask is a lot of water, which is neutral, a lot of dissolved salt, which is neutral, right? So you splash in like a thing of base so that it's going to temporarily flash pink, because in that area of the solution, the indicator thinks that like we have an excess of base in that area. However, like you kind of take it, you kind of swirl it around, and it turns out, oh, okay, there was enough acid in there somewhere for that base to react with, because there was still some acid present that was there, right? But you're going to start getting flashes of pink when you're getting really close to having no more acid molecules left in that flask. So when it starts flashing pink, you're going to start being really careful, because like at that point we're talking about there's hardly probably any acid left over. And depending on how concentrated your base is that you're putting in, right, you're reacting those. In this case, it'd be like a 1-to-1 particle ratio, right? But let's say this is super concentrated and we're at the point when there's hardly any acid left. One really concentrated drop of this could actually be enough where like all the acid is completely eliminated. If you put a strong base in here, one drop can mean that there is a ton of excess hydroxide, and that solution is going to turn pink like this, and then you've gone too far. And the reason that's important for us to know is because like we have to know the exact amount of this that we use to neutralize it. So if you end up overshooting it and turning this guy pink down here, right, then you're not going to have the accurate reading for the exact amount of base it took. And if we don't know the exact amount it took, then it's going to be harder for us to actually figure out this identity, this concentration, so on and so forth. So this is kind of like a brief introduction of what we're going to be doing with this. I'm probably going to start another video kind of going more in depth and maybe do like an example of like how we would use some of this information in a lab setting. And I'm going to make that video right now, but this is kind of, again, just serving as like an introduction to titrations and what we're doing. And the whole point, again, is to try to neutralize something. And if we don't know anything about this acid or its concentration, right? Like if you knew that concentration, you'd know exactly how much base to add. But the whole point of this is like we have a mystery acid or base, right? Which is like really similar to how it is in real life, right? You work at a water plant. The whole point is for you to test how much acid is present in the water right now, or how much base is present in the water, right? And are they at healthy levels? But the whole point is you guys don't know how much, like what the acidity is or what the alkalinity is. So they have to do titrations to actually figure out the exact concentration of like the acid in the water or the base in the water. So we're going to kind of keep it relevant to real life and make sure that like we're keeping the concentration unknown, possibly the identity unknown, and other things unknown. But you will have total 100% control of the volume, because you actually have to measure that to actually put it in here. So I'm going to make another video now kind of, again, explaining, let's pretend that we did this, right? What does that information tell us, and how could we use that to identify this unknown acid and or base?